Then let's record. Okay, perfect. So everything is all set and we're ready to continue on with the lecture. Can everyone hear me in the back? Okay, I'll try to speak as loudly as possible. If you're having trouble hearing me, please don't be shy to move up. Especially if the ice machine gets going, I may end up yelling at the people in the front of the class, trying to have the back of the class be able to hear me. Give me one moment as there is I need to close and reopen this note set. Give me 1 second. I apologize for that delay. It's a mild technical glitch. Give me 1 second just to reopen the note set. It'll be open in about 1 second. Okay, perfect. Okay, perfect. So in this next section, we're going to be talking a little bit about units of measurements, and I'll be making a joke at engineers' expense, but this really is a really interesting lesson to learn from when students ask, why do we care about units of measurement? Well, units provide meaning to numbers. Numbers do not have an inherent meaning or correlate to quantities in our physical world. Units provide meaning to numbers. What do we mean by 10? We mean 10 meters. We're describing units of distance. We're describing something that we can see and observe in our physical world. So units provide meaning to numbers by indicating what are you measuring: distance, time, mass, force, etc. And what standard unit of measurement are you using? I know for the majority of you, we're all brought up unfortunately, on the English or imperial unit of measurement system. Science primarily uses the metric system. And this really came to head in this hilarious story, and it really helps you understand, why do units matter? You may be wondering, what exactly is this picture representing? Well, this is the crashed $125 million Mars rover. This was quite an infamous incident, and I always like to ask, is it 10 feet or 10 meters below the surface of Mars? So the main excerpt from the article that I thought was really interesting, the software calculated the force and thrusters needed to exert in pounds of force. This is the English or imperial unit. A separate piece of software took in the data assuming it was in the metric unit of newtons. So failure to convert units created a bit of a problem. Propulsion engineers typically express force in pounds, but it was standard practice to convert to newtons for space missions. Just out of curiosity, 1 pound is about 4.45 newtons. Don't need to worry about that. This last sentence really helps summarize the habits I want to enforce with my students, and that engineers at NASA's Jet Propulsion Lab assume the conversion had been made and didn't check. So it's not just failure to convert the units, but failure to check and audit one's work. Check your work, and it can save you from pretty disastrous events. Okay, so let's talk a little bit about metric to metric conversion. The metric system is really beautiful in that it is built on powers of 10. So the reason why we spent a lot of time talking about scientific notation and how to handle exponents is because metric to metric conversions are built on multiplying powers of 10. So this is why we love scientific notation, because scientific notation is built on powers of 10. You know, your 1.0 times 10 to the third. We are handling powers of 10. Now, the metric system is built on what are known as base units, and there are 5 base units that you will see a lot in this class. So for distance, we're referring to meters. Meters is the common unit of distance. Mass is commonly expressed in grams. So if you're curious about the distinction between mass and weight are identical on the surface of Earth, but when you get into space, we'll start to talk a little bit about why the English or imperial system has a lot of trouble handling units of mass. Anyway, so grams, and it's considered interchangeable with weight for most chemistry experiments. Time is in seconds, volume is in liters, and temperature is in Kelvin or Celsius. The reason why I push for you to think of temperature in terms of kelvins, it is the primary unit of temperature we'll be using for most chemical calculations. Celsius, I like to think of as the practical unit. It's the one that's most easily measured, but Kelvin is the one that we actually plug into equations. Now, the beautiful thing about the metric system is it's built on the idea of taking a base unit and then modifying it using common prefixes, each with a unique symbol. These prefixes are universal and can be applied to any base unit. So the prefix modifies the base unit to give a new prefix unit. And each of these prefixes corresponds to a power of 10 quantity of our base unit. So the prefixes are essentially describing very large or very small amounts of our base unit. So for example, centimeters. See this little c here? A centimeter corresponds to 10 to the negative second meter, or a very, very small amount of meter base units. So this centi prefix is encapsulating and describing this power of 10. Does that make sense? Does everyone see how to go from a prefix to a base unit? All we have to do is replace the prefix with its power of 10. That's what makes metric to metric conversion so easy. We'll be doing some practice on this. For example, a milliliter, the milli prefix corresponds to 10 to the negative third. So if we wanted to go from milliliter to liters, we just replace the milli with the power of 10. So is a milliliter describing a large or small volume? Small. How do we tell? Is a power of 10 positive or negative? Negative. It's a small power of 10. It's a small unit of measurement. Okay. Now, to talk a little bit about how to convert a prefix unit into a base unit. The reason why I boxed this table is you are expected to memorize this table. You will not be provided the prefix conversions on the exam. You will eventually become so used to these conversions, you'll be able to do them instantly. I would highly suggest if you had to prioritize a few, you should know milli, kilo, micro, nano, pico, and centi, as these are the primary prefixes we'll be using in this class. You should know all of these prefixes, but if you had to prioritize, I would start with this set. Okay, now to convert a prefix unit to a base unit, you simply replace the prefix with a power of 10. So for example, if we have 657 millimeters and we want to convert it to meters, what is our prefix in this case? Milli. The small m, this little m, corresponds to the word milli, the milli prefix. And what power of 10 does milli correspond to? Yep, 10 to the negative third. So we replace our small m, our prefix, with 10 to the negative third. Okay, and can we compute this out longhand? Do we know how to handle multiplying by powers of 10? Have we done that before, just a few minutes ago in lecture? Yes. So all we have to do is take 657. So times 10 to the negative third, we put our decimal point at the end, and what direction are we moving our decimal point? To the left or to the right? Left. And how many spaces? 3. 1, 2, 3. So we have 0.657 meters. Not too bad, right? This is known as a one-step conversion. I'd like you all to attempt this next conversion. I'd like you to go from 457 kilograms, and I'd like you to tell me that corresponds to how many grams. And I'm going to zoom up a little bit so you can see what the kilo prefix corresponds to. So, just as a side note, the library also has a calculator rental service where if you provide your ID, they can provide you a calculator in case you happen to forget it on a lecture day. Okay, so continuing on, looking at the kilo prefix. So looking at our table, K, kilo corresponds to what power of 10? Yep, 10 to the third. So we have 457 times 10 to the third. This corresponds to our kilo prefix, grams. So if we wanted to write this out in proper scientific notation, would someone like to propose our final answer in scientific notation? Yep, 4.57. Very close, 10 to the fifth. 10 to the fifth. If you enter this calculation into your calculator and then have it convert the number into scientific notation, you'll get out the following result. If you're curious how we obtain this result, first and foremost, we have a power of 10 to the second here in 457, and we just added these two exponents together. We'll talk about that in a moment. And of course, don't forget to include that it's in grams. When you do unit conversions, don't forget the units. Any questions on this example? Okay, let's continue on. Now, here's a key fundamental concept, and this is the basis for unit conversions. And let me switch to a different pen color for this. Different units and numbers can describe the same quantity. For example, in the following picture, we are comparing centimeters and inches. So if we look at centimeters and we compare the quantity of 2.54 centimeters to the quantity of 1 inch, looking at the red line, are these two quantities describing the same distance in our physical world? Yes. So we have a different number and unit describing the same quantity, the same distance in our physical world. This is why unit conversions work. This is how we can go from one number in unit to another number in unit and still be describing the same thing in our physical world. Okay, so as a result of this idea, you can write unit conversions as a ratio of two equal quantities. So for example, we know 2.54 centimeters are equal to 1 inch. Now, from algebra, we know that we can take both sides and we can divide them by the same quantity and end up with the same equality. So I'm going to divide both of these sides by 1 inch. Okay? And that gives us, we have 2.54 centimeters over 1 inch, and that's equal to 1. What this is saying is that these two quantities are equal, and they're equal to 1. The ratio is equal to 1. Does that make sense? Okay, so this is the mathematical basis for why unit conversions work. Now, a key principle from math is you can multiply any quantity by 1 and the quantity is unchanged, right? In unit conversions, what we're doing is we're multiplying by 1, a ratio of 2 equal quantities, and the units and number will change as we convert to different units. So to give you a classic example of this, we all know that 2 times 1 is equal to what? 2, right? You can multiply anything by 1 and you get the same quantity out. Now, just as a side note, when multiplying and dividing, the units cancel just like normal numbers, right? So if you have 7 times 2 over 7, we have 2 quantities that are the same on the top and bottom of our dividing line. So we all know what's 7 divided by 7? 1, right? They cancel. Likewise, if we have 2.54 centimeters per inch, if we have inches over inch, how do we handle 2 equal quantities? Do they also cancel? Yes, the units cancel just like normal numbers. So our goal in unit conversions is to cancel out our starting undesired units and retain our desired ending units. And to do this, we multiply by what is known as a conversion factor, which is essentially a fancy way of writing 1. Does that make sense? Okay. So just a side note, one thing that I see that's super common in unit conversions that's especially problematic is make sure that your units cancel and that you write out all of the units. We're going to talk about composite units later on in this lecture, but for example, when you have 5 centimeters squared, this square is telling us that, just like before, when we have an exponent, the exponent indicates the number of times the base is multiplied by itself. So what do we have here? When we have centimeters squared, what is that telling us? Yep, centimeters times centimeters. So centimeters squared is centimeters times centimeters. Does everyone see how there are 2 centimeter units now? Because it's centimeters squared. So when we're doing unit conversions, you need to make sure both of these actually cancel. We'll see this in later sections. Okay, so let's talk a little bit about how to convert from one unit of measurement to another. So first and foremost, I'm asking you, how many milligrams are in 3.46 times 10 to the first kilograms? Okay, so the first step in any process is identifying your problem. So first and foremost, what units are we starting from? Kilograms. In general, your starting units are given by the quantity containing a number and a unit. We know the amount of kilograms we're starting from. So we're starting with 3.46 times 10 to the first kilograms. The next step is to indicate what units we are trying to convert to. So what's our end goal here? Milligrams, yep. So we are trying to go from kilograms to milligrams, okay? Now, as a general rule of thumb, it's not best to go from prefix to prefix unit. Instead, the most secure method of performing unit conversions is to go through the base unit. So what is the base unit in this case? What is the base unit? Grams, exactly. It's the unmodified unit. So notice these two, kilogram and milligram, are prefix units, modifying the base unit of grams. Okay, perfect. So our goal is to go through the base unit. And the reason why we go through the base unit, do we know how to convert from prefix to base unit really easily? Do we have a giant table that we discussed? We have this giant table right here that you're going to become quite acquainted with. And this allows us to go between prefix and base units really easily. Okay. So to execute upon this, we convert from the starting prefix unit to the base unit. So we went from kilograms to grams. Finally, we go from the base unit to the desired ending prefix unit. So grams to milligrams. This process minimizes error and ensures you don't have to do any extremely complicated conversion factors. Okay, so just to summarize, we're going from kilograms to grams to milligrams. I always like to make these problem-solving maps because it helps me organize my thoughts. Okay, so to this end, we have to identify a conversion factor containing the desired base unit and the starting prefix unit. Okay, perfect. We have our rules in place. In order for the units to cancel, your desired base unit will be on top and the starting prefix unit will be on the bottom. So let's show what I mean. If in the first case, we want to go from kilograms to grams, okay? What's our relationship between kilograms and grams? 1 kilogram corresponds to how many grams? 10 to the third. You have the reference table in your notes, and I encourage you to use it when necessary, but try to recall these conversion factors from memory. It's going to take a lot of practice. Okay, so as we see, we've correlated the kilo prefix to 10 to the third. We have an equality. Our next step is to make a conversion factor. So if we're going from kilogram to gram, what unit is going to be on top? Grams. So we're going to make a ratio with grams on top. So we have 10 to the third gram. And what's going to be on the bottom? Kilogram. Does that make sense how it works? Your arrow points in the direction of what unit you need on top. Okay. So as a general rule, your power of 10 will always be with the base unit. I see students make this mistake a lot. They put the power of 10 in a random location and they end up with the wrong result. The power of 10, this 10 to the whatever, stays with your base unit at all times. Okay? Let's try a more complicated example. If we're going from grams to milligrams, so 1 milligram corresponds to how many grams? What does the milli prefix correspond to? 10 to the negative third. To help everyone along with this, I'm going to scroll all the way up to the table. So reading from the table, what power of 10 does the milli prefix correspond to? 10 to the negative third. Okay, perfect. So we have 10 to the negative third gram in 1 milligram. Now, looking at this conversion, we're going from grams to milligrams. What units need to be on top? Milligrams, exactly. Because what are we trying to end at? Milligrams, exactly. So 1 milligram goes on top for how many grams? Yep, 10 to the negative third. We're just reading off this equality. Does that make sense? Okay. So the final step, now that we have all of our conversion factors in place, is all we have to do is multiply by the unit conversion factors. So let's find our starting number since, okay, so we have 3.46 times 10 to the first. So let me write that in purple. Okay, and now all we have to do is multiply by our conversion factors. Okay, so we know that there are 10 to the third gram per 1 kilogram. And as we notice, do kilograms cancel? Yes. Okay, and for our next step, we have 1 milligram over 10 to the negative third gram. Do grams cancel? Yes. What final units are we left with? Milligrams. Okay, perfect. Now, we can process these powers of 10 in 2 ways, but we can just do this by hand. by adding up our exponents. So in general, if you have a positive power of 10, you're going to add your powers of 10 together. If you have a negative power of 10, you're going to subtract. However, we have 3.46 times 10 to the first times 10 to the third times 1 over 10 to the negative third. And this is all in milligrams. So my question to all of you is, if we're adding these powers of 10 together, what do we need to do first to this negative exponent? So what's 1 over 10 to the negative third correspond to? If we're dividing by a negative exponent, that's the same as, yeah, you can subtract the negative, or we can just move it to the top, right? Yeah. So we take our 3.46 and we have 10 to the first plus 3. And then as our classmate pointed out, when you divide by a power of 10, you subtract the power. So we're subtracting negative 3. That in turn gives us 3.46 times 10 to the 7th milligram. Does that make sense? You can also do this with your calculator, but I encourage you to be used to quickly adding and subtracting powers of 10, as it saves you a lot of time on exams. If you want assistance on how to enter this specific operation to the calculator, we'll be doing a few in the later portion of this class. Okay, now I'm going to let you loose on the following example. I'd like you to tell me how many microliters are in 153 milliliters. And I encourage you to set it up procedurally, and please do not skip steps. Any questions? Yes, that's about any questions? Yeah, looks perfect. Any questions? Okay. So if the power of 10 always stays with the base. Okay. Yes. Yeah. Okay. Any questions? Okay. Any questions? Yep. Your math looks good. Oh, wait. I noticed for this one, the math is good, but it's in the opposite direction. We're starting with 152 minutes. Oh. So going to what was calculate. Any questions? Yeah. That's perfect. Any questions? And I'm going to set up the document cam really quickly so we can enter some data into the calculator. So continue working on the problem, and then we'll come together to discuss for approximately 1 minute. Sorry for that mild interruption. Okay, how's everyone doing so far? I saw a lot of reasonable setups. Anyone have any questions before we talk about the solution? Okay, so let's start with a map. What units are we starting from? Milliliters, yep. So we're starting from milliliters. And what is our end goal? Microliters, yep. Okay, so what is our intermediate step? What intermediate units do we need to go through? Liters, exactly right. We always go through the base unit. Okay, so with that said, we now need to make some conversion factors. So 1 milliliter corresponds to how many liters? What does milli correspond to? Yep, 10 to the negative third. Perfect. Okay, continuing on with this idea, 1 microliter corresponds to how many liters? What does the micro prefix correspond to? Yes, micro is 10 to the negative 6. Does anyone have a question on where I got this 10 to the negative 6 from? Everyone knows we're getting this from the table, right? Okay, perfect. So in our next step, what we need to do is we need to take these equalities and convert them into a meaningful unit conversion factor. Okay, so if we're going first and foremost from milliliters to liters, so what units need to be on top? If we're going from milliliters to liters, what needs to be on top? Liters, exactly. So we're going to write 10 to the negative third liter per 1 milliliter. Good, good. And if we're going from liter to microliter, what units need to be on top? Microliter, exactly. So we know 1 microliter, whoops, per how many liters? Yep, 10 to the negative 6. Okay, perfect. We have all of our unit conversion factors set up pretty quickly. And now all we have to do is take our original number and plug it in. So we have 153 milliliters. Milliliters cancel, liters cancel. And I'll showcase how to do this in your calculator. Allow me to tab to the document panel. Okay, so first and foremost, we are starting with 153. So I enter 153. Everyone have that entered into their calculator? You're next going to hit the EE button, this EE button right here. Okay, perfect. Now, looking at our expression, what's the first thing that we're multiplying by? What power of 10 are we multiplying by? Negative 3. Okay, so it should be EE. We enter a 3, and then you hit the sign change button right down here. If you did everything properly, there'll be a little negative sign in front of the 3. Does everyone see that little negative sign? Okay, you hit equals, and this is the result of the first step. But we aren't done. What's the next step? Are we multiplying or dividing by? We're dividing by. So we need to hit the division symbol. So you're going to hit the division symbol. Okay. And then you're going to hit 1 EE. And then what is our power of 10? What is our power of 10? Negative 6. And we already know how to enter negative powers. You hit the 6 button. And then you hit the negative sign. Then, once you're done, you hit the equal sign, and you should get the following result. Now, if you want this in scientific notation, you hit the second, the green button, and then the number 5, which has a little science above it. And you should get 1.53. And what does this 0.5 tell us? What is that number representing? Scientific notation. So what's our power of 10? What's our power of 10? To the fifth. Fifth, exactly. Okay. So we have 1.53 times 10 to the 5th microliters. So a microliter is a relatively small quantity. Okay, perfect. So with that guided example covered, I'd like you to tell me how many nanograms are in 457 micrograms. So take a moment to compute that, and I encourage you to practice using your calculators. The more you practice now on these relatively straightforward problems, the more you'll be able to use your calculator for complicated. I see a lot of reasonable responses, and essentially all of chemistry is just different types of unit conversions. In this class, the majority of the calculations you'll be doing can be boiled down to unit conversions. So what are our starting units? What units are we starting from? Micrograms. The reason why this is our starting units is it has both a number and a unit provided. So we are starting from micrograms. Okay? Now, what is our end goal? What units are we trying to reach? Nanograms. So we're going from micrograms, and our end goal is nanograms. So what intermediate units are we going to go through? Grams. Okay, perfect. With that established, we are now ready to start generating conversion factors. Allow me one moment just to get the charger. I'd like you to take a moment and try to set up the conversion factors, and then we'll discuss this in a class in about 2 minutes. Okay, so looking at our conversions, in our first step, we're going from micrograms to grams. So 1 microgram corresponds to how many grams? What power of 10 does micro correspond to? Yep, 10 to the negative 6. Okay. We're next going from grams to nanograms, and 1 nanogram corresponds to how many grams? 10 to the negative 9th. Good, good. Okay. So in our next step, what we're going to do is we're going to generate a valid ratio of these 2 units known as a conversion factor. So in this case, if we're going from micrograms to grams, what units need to be on top? Grams, exactly. So we have 10 to the negative 6 gram. Remember, the power of 10 always stays with the base per 1 microgram. Okay, and in our next step, we're going from grams to nanograms. So what units need to be on top? Yeah, so we have 1 nanogram over 10 to the negative 9th gram. Perfect. So we have both of our unit conversion factors. The only thing we need to do in the end is plug in our starting number with units. Perfect. And we can do this with our calculator. So let's switch over to the document camera for that. Okay. So first and foremost, we're starting off with what number? What number are we starting off with? 457. So our first order of business is to enter 457 into our calculator. 457. Okay. Now, what are we multiplying 457 by? Negative 6. 10 to the negative 6. So in order to do that, we're going to hit the EE button. 457. EE, and then 6 negative sign. If you hit these buttons correctly, again, you're going to hit EE, 6, and then the sign change button. You should see the following in your calculator. Can I get a thumbs up if you got that in your calculator? Okay, perfect. So then you hit the equal sign, and the first step is complete. Okay, so if you did the first step correctly, you should see the following number in your calculator. Now let's do the second step. 1 nanogram per divided by 10 to the negative 9th gram. So are you multiplying or dividing by that quantity? Dividing. So we need to go into our calculator and hit the divide button. And then you hit 1 EE 9 sign change. You should see the following in your calculator before you push the equal sign. Everyone okay so far? Then you hit equals, and you should get the following number out in your calculator. Okay, for the next step, you're going to hit 2nd and 5 to convert it to scientific notation. And lo and behold, we have 457 times what power of 10? 10 to the 5th. Okay. Perfect. So all we have to do is write that down. Any questions on this example? If you're having difficulty utilizing your calculator, please do not be shy to bring questions or bring your calculator with you to office hours. If you do not know how to use your calculator, you're severely constrained into how readily and how quickly you can solve problems in chemistry. Okay, any other questions on this example? Okay. So what we're now going to do are perform unit conversions on composite units. And composite units are a little bit of a step up. And let's talk a little bit about composite units. So composite units are a unit of measurement that contains 2 or more base units. So now we're combining base units in ratios or multiplying base units together. So for example, density is expressed in gram per milliliter. Just in terms of language, when we say per, what is that telling us to do? Multiply or divide? Divide. So it's per mil, grams divided by milliliters. Volume is an interesting composite unit. So volume isn't a base unit. Let me rephrase. Volume can be expressed as both a base and a composite unit. So volume can sometimes be expressed in centimeters cubed. So the relationship is a centimeter cubed is equal to a milliliter. We'll talk more about that when we discuss density in detail. Remember, what does this centimeter cubed represent? What does centimeter to the third tell us? We have how many centimeter units multiplied together? 3. Yeah. Let me write it below. Centimeter times centimeter times centimeter. Okay. Now, continuing on with this idea, to convert composite units, there are a few rules that are a little bit different. So in this case, for example, if we're converting 430 microgram per mil into milligram per microliter, here are the steps involved. You handle each unit in the composite unit separately, identifying your starting and ending units. Just like before, you're going to go from the prefix unit to the base unit, and then from the base unit, you go to your desired ending prefix unit. You always go through the base unit when doing unit conversions. So, for example, in this case, what are our starting units? Let's identify each of them separately. What's our starting unit set? Micrograms. So we have micrograms on top. And then what do we have on bottom? Milliliters. So we have micrograms as our first starting unit. And instead of milliliters, we have 1 over milliliters. Now, there are a few ways to go about handling this. And the simplest way, at least while you're starting out, is just to look at the milliliters individually. So we have micrograms and milliliters. And let's just think, how do we convert these units? So with that established, so you have micrograms divided by mils, our goal is to identify a conversion factor containing the desired base unit and the starting prefix unit. Now, as a general rule, and this is what changes when you start to deal with ratios, in order for the units to cancel, they must be on opposite sides of the dividing line. Okay. So we're going to try to make a conversion factor containing our desired unit in the same location as in the final answer. And we're going to choose a conversion factor containing our starting units on the opposite side of the dividing line. A lot of words, let's show how this works in practice. So if we have microgram per milliliter, okay? So looking at the top, we're going to need to go from micrograms and looking at the problem, what is our final units? What's our final end goal? We're going from microgram to what? reading the problem? Milligram. So we're going from microgram to milligram. Okay. Additionally, we have on the bottom milliliters, and our end goal is what unit of volume? Microliters, exactly. We're just reading off our objective. Okay, perfect. So what is the base unit for microgram and milligram? What's our base unit? Grams, yep. What's our base unit for milliliters and microliters? Liters, okay. Okay, perfect. Now from here, we're going to have to generate some conversion factors. And this time, I'm going to ask you to try to generate them a little more efficiently. So first and foremost, if we want to go, and let's just be reflective of the fact that it's 1 over mils, and so we need 1 over our volume units. Okay, so first let's start with the top, micrograms to milligrams. So my question to all of you, if we're going from microgram to gram, how many grams are in a microgram? 10 to the negative 6. Why do we have grams on top? Where are we going to? Grams. Why do we have micrograms on the bottom? Where are we starting from? Micrograms, exactly. Okay. Next, we're going from grams to milligrams. What units go on top? Milligrams. So we have 1 milligram. And what units go on the bottom? Grams. What power of 10 is associated with that milli prefix? Yep, 10 to the negative 3. Okay. Now for a bit of an interesting situation. What units are we starting off with on the bottom? Is it milliliters, or do we have 1 over milliliters? 1 over milliliters. So then, keeping in mind we're starting with microgram over milliliters. In order for milliliters to cancel, where do we need to put milliliters in our conversion factor? On the top or on the bottom? On the top, exactly. We need to have milliliters on opposite sides of the dividing line. So we need milliliters on top. Does that make sense? Okay. So if we're going from 1 over mils to 1 over liters, what units do we need to have on the bottom? What units do we need to have on the bottom? Liters, right? Does that make sense? Okay. So in 1 milliliter, that has how many liters? Yep, 10 to the negative 3rd. Okay, and then finally, if we're going from 1 over liter to 1 over microliter, in order for liters to cancel, where do we need to put liters in order? In order for liters to cancel? On the top. They need to be on opposite sides of the dividing line. And where does microliters end up? On the bottom. And that's where we want it in the final answer. Right? We want, in the end, milligram per microliter. So we have microliter in the right spot. Okay. Now, how many liters are in a microliter? Yep, 10 to the negative 6. Perfect. Let's check our units now. So grams cancel. Okay. Milligrams are right where we want them. Micrograms cancel. Milliliters cancel. And liters cancel. So do we have milligram per microliter? Is it in the right spot? Yes. So all we need to do now is go to the original problem, find our number, 430, and plug it in. So we're going to plug in 430 into this expression. Notice how, for unit conversions, we're really just looking at the units. The number is added at the end. The number is just whatever we start punching into our calculator. Okay, now let's switch to the document CAM and let's discuss how to punch this into your calculator. So what number are we starting off with? 430. So lo and behold, we're going to enter 430 into our calculator. Okay, for our next step, what are we multiplying by? What power of 10? -6. So we're going to enter 430 EE6, and then we're going to hit the sign change button. If you hit equals, this is what you should see in your calculator. Does that match? Okay. So now for our next step, what are we dividing by? What power of 10 are we dividing by? -3. Okay. So we're going to go to our calculator and hit the divide button. And we're going to go 1 EE -3. And if you hit your calculator equal sign, you should get the following results. Everyone good so far? Okay. So let's continue on. What are we dividing by next? 10 to the -3. Okay. So we're going to go to our calculator and go divide by 1 EE -3. So you should get 430 at the end of this next step. Everyone good with that? Okay. Finally, what are we multiplying by? 36. Yep, 10 to the -6. So we're going to go to our calculator and go E times 1 EE -6. And if you punched everything in your calculator correctly, you should get the following result. If you convert it into scientific notation by going second side, you should get 4.3 times 10 to the -4. I would highly recommend following along when we do these calculator inputs, as common calculator errors will result in point deductions on quizzes and exams. So just to clarify, our final answer in this is 4.3 times 10 to the -4. And then the units are milligram per microliter. So this is a typical conversion that you have to do as part of calculations in chemistry. Any questions? Okay, I'm going to let you loose now. Actually, we're going to talk about one more type of composite unit before I have you work on some problems individually. So cubic and square units are a unique type of composite unit. And the key feature for these is you need to make sure to convert each component of a cubic or square unit. So for example, when I'm asking how many centimeter cubed are in 150 millimeter cubed, first and foremost, let's identify our starting units. What are our starting units? Millimeters, and more specifically, millimeters cubed. Exactly. So we're starting with 150 millimeters cubed. And what is our end goal? What units are we working towards? Yep, centimeters cubed. Now, what is our intermediate base unit going to be? More than just meters, meters cubed. It's okay. Okay. Now, from here, let's think a little bit about our conversion factors for a moment. So, ignoring the cubes for just one moment, 1 millimeter corresponds to how many meters? Yep, 10 to the -3. Okay. Now, the best way to handle cubic units, in my opinion, is to generate your conversion factor first and then modify it based on the power. We'll talk about that in a second. So 1 centimeter corresponds to how many meters? Centi, what does that prefix correspond to? What was that? Yep, -2. So it's 10 to the -2 meters. Perfect. Now, just like normal, if we're going from millimeters to meters, what goes on top? Meters, yep. So we have 10 to the -3 meter per 1 millimeter, okay? Now, keeping in mind that this is millimeter cubed and meter cubed, the fastest way to complete this conversion is to just cube this ratio. And I'll show you how to do that with your calculator. Okay, let's do the same thing. We're going from meter cubed to centimeter cubed. So what goes on top? Centimeters, yep. So we have 1 centimeter over 10 to the -2 meter, and then we cube it. Okay. Now that we have all of our conversion factors in place, all we have to do is input our original number. So the only thing that's changed in this process is that we now are cubing our conversion factors because we have a cubic starting unit. Does that make sense? Okay. The process for generating these conversion factors is exactly the same as before. Now, let's break out our calculators. And the first thing I want everyone to tell me, what is our starting number? 150. Okay, so we have 150. Now, we are multiplying by what? What power of 10 are we multiplying by? 3. Yeah, 10 to the -3 cubed. Now, there are two ways of going about this. The primary way to handle cubes when you're dealing with powers of 10 is you multiply these two powers together. So what's 3 times 3? 9. Likewise, what's 2 times 3? 6. Now, there's a slightly more efficient way using your calculator that's more general. And I'll show you how to enter this and make sure to follow the keystrokes carefully. So first and foremost, you're going to hit the times button. So you're going to hit the times button here, and then you're going to hit parentheses. You should see a 0 up here. That's normal. Now, what we're going to enter is the same input for 10 to the -3. Okay? So we're going to enter that input. So we're going to enter 1 EE -3. So you should see this in your calculator. Now, do not hit equal sign. What you're going to do is you're going to hit the close parentheses button. Okay? And you should see the following pop up in your calculator. Does that match? Okay. Next, what you're going to do is you're going to find the cubic button. So the cubic button is obtained by hitting second and then 1. If you notice below 1, does everyone see that little x cubed below 1? Okay, so you're going to hit second, the green button, and then 1. And if you did it properly, you'll see this large number appear. Everyone good so far? You're then going to hit the equal sign. And if you did everything properly, you should see the following number appear. Does that match? Okay. So for our next step, what are we dividing by? Yeah, 10 to the -2 cubed. So this time, you're going to hit the division button. And then you're going to hit the open parentheses button, and you'll see a 0 again. Everyone on board so far? Yes. Sorry, what? So I'll showcase each step up to this point from the beginning. So we enter in 150. Then we hit times and parentheses 1 EE, in this case, -3rd. We then close our parentheses, and then we hit second followed by 1, and that cubes our number. Are we on track so far? Okay. Then you hit the equal sign. We're at this point. Now we can divide by our next number. You hit divide, then the open parentheses. You should see a 0 appear. Now we're going to enter in the input for 10 to the -2nd. So to do that, we're going to do 1 EE -2nd, and we're going to close our parentheses. And you should see the following number pop up. Everyone okay so far? Next, you're going to cube it by hitting second followed by 1. And the following number should appear. To end this operation and complete the division, you're next going to hit the equal sign, and the following number should appear in your calculator if you did everything correct. Does that make sense? Okay. So with that said, you just get out 0.15. Okay, perfect. Any questions on this example? Okay, let's have you work on some problems in groups. So let's tackle the first one. I'll write it out in larger writing so that way everyone can see. 350 kilograms per milliliter is equal to how many micrograms per kiloliter? You'll notice a lot of our ratios have to do with mass over volume because that's often where you'll be doing these conversions. Any questions? Yes. Yep, it's going to be quite a large. Yeah, that's right. Any questions? Oh, try looking at each of them individually, just like you do it. And then the only thing that's new is on the bottom, it's 1 over the rule. Yes. Yep. But try to treat them as like separate cases just to make it easier to set up. is referred. So if I cover these up, go to it's one over.
Okay, so then we would be another set.
Yes, exactly.
I wrote it down. Well, you can write down the steps and reason I wrote is to what all poses.
Oh.
So that if you want to write it down, so that when you calculator. So it's something. No, I believe it.
Okay. We use micro. Right? Micro is -6. Yes. So, okay, that's right. Wait, that's right. So we're going to go and down to meters and then meters to millimeters. Yeah. And then meters to yeah. Okay. So 1 and 9 is 1,000 meter or 2,000 meter. No, the other way around. Yeah. What's because yeah, you're right. But I did it. And then 10. No, 3. Kilo, yeah. Yeah. But that was meant. We'll just finish it and then we'll.
How's everyone doing so far? And then we need a little bit more time on this exam?
Yeah.
What about here?
Did you get 2.5 1 times 10 to the 17?
Yeah.
He makes one, right?
That's what I got.
I didn't like
I don't know if it's but that's fine.
I know. This is a lot. Okay, to bring everyone together for this example so we can ensure that we have the same methods. Now, while you're learning this process, there is a method that you can utilize, though I do not recommend it as it's not general. Like it's good for these types of problems, but I'd like you to do these conversions the same way I do because it'll save you a lot of hassle when we start doing chemical calculations and stoichiometry calculations. Well, but for now, the way that you can think about these conversions as if you're taking, you can think about it as if you're taking kilograms and going from kilograms to grams to micrograms. This is on the top. And then on the bottom, you're going from 1 milliliter to liter to kiloliter. And then in the end, all you do is take the result from the top and divide it by the result from the bottom. This method is fine for now, but I really want you to get in the habit of setting up conversion factors for these composite units. And that's what I will showcase right now. Okay, so with that said, let's showcase how to do that. So first and foremost, we have starting units of kilogram per milliliter. Okay, perfect. So I can separate this composite unit into kilograms and 1 over milliliters. So what's our end goal for the top? We're going from kilograms to what? Micrograms. Yep, we're going from kilogram to microgram. So what is our intermediate unit? Grams. Yep. Okay, we have 1 over milliliter. And what's our end goal in this case? Kiloliter, or more specifically, 1 over kiloliter. So what's our intermediate base unit? Yeah, 1 over liters. Yep, perfect. So we have our guideline set up. So our next step is to execute on that guideline. So I'm going to write out our starting input. So we have 350 kilogram per milliliter. And let's start with the top. What do we need to have on top in order to end up with units of grams on top? Grams, yep, so we need grams on top. And in order to cancel out these kilograms, what units need to be on the bottom? Kilograms, yep. So you set up your conversion factor so the undesired units are on opposite sides and the desired units are in the same location as in the final answer. So how many grams are in a kilogram? Yep, 10 to the third. Just as a reminder, the power of 10 always stays with the base unit. Okay, for our next phase of this process, what do we need on top? What do we need on top in the end? Micrograms. So micrograms needs to go on top. And what units need to be on the bottom? Grams. The reason why I'm encouraging you to use this method is in many cases, you're going to have to figure out in later portions of this class, what exact conversion factor do I need to use to cancel out my undesired units and reach the desired final answer. The majority of chemistry is just unit conversions. Now, in 1 microgram, we have how many grams? 10 to the negative 6. Okay, perfect. We're all set in that department. Okay, now for our next step, we have milliliters on the bottom and we want kiloliters in the end, right? So then, in order to cancel out milliliters, where do I need to put my unit of milliliters? On the top or the bottom? On the top. They need to be on opposite sides, so they cancel. Okay, and in 1 milliliter, that corresponds to how many liters? Yep, 10 to the negative third. Okay, finally, what ending units do we need on the bottom? Kiloliters, yep. And in 1 kiloliter, in order to, what undesired unit do we need to cancel? Liters. So we put liters where? On top. So how many liters are in a kiloliter? 10 to the third. Okay, perfect. All of our units cancel and we're done. Does that make sense to everyone? If you can generate these conversion factors quickly, all you're doing is changing which portion of the conversion factor is on the top and which one's on the bottom to cancel out your starting units and to reach your desired units. As a side note, please do not go from prefix to prefix. Oftentimes when students try to cut out steps from this process, they make mistakes. It doesn't work well. Okay, now let's enter this into our calculator. Let's enter this into our calculator. So what are we starting out with? What number are we starting out with? 350. Okay, so we have 350. Okay. And then what are we multiplying it by? What power of 10 are we multiplying it by?
3/3.
Yeah, 10 to the third. Okay. So what we're going to do is hit EE3, and you should get the following number. Again, you're hitting EE and then the 3 button. Okay, what are we dividing by now?
10 to the negative 6.
10 to the negative 6. Okay, so to accomplish that, we're going to hit the division button, and we're going to hit 1 EE negative 6. 1 EE negative 6. And then you're going to hit the equal sign. If you did everything correctly, you should get the following number. Everyone good? Okay, so continuing on, we are now going to divide by what quantity? 10 to the negative third. Okay, so to accomplish that, we're going to hit divide and then 1 EE negative 3. And you should get the following result if you've been following along correctly. Any questions? Don't be shy to ask. You want to make sure you're able to use your calculator. Okay. Finally, we are multiplying by what power of 10? 10 to the third. Yeah. So what we're going to do is we're going to hit times and then 1 EE 30. Okay, then you're going to hit the equal sign and you should get the following result if you did everything correctly. What power of 10 do we have here? 17. Yep. Okay, perfect. So we have 3.5 times 10 to the 17. And what are our units? Don't forget the units. Microgram per kiloliter. Okay, perfect. Any questions on this? Okay. So I'm going to have you attempt the following problem on your own again. So I'd like you to convert 170 centigram per millimeter cubed to milligram per centimeter cubed. So remember the setup is correct. Any questions? Okay. Any questions? Yep, the first part looks good. Yeah, and instead of remember to write the conversion factor and then cube it. So do the same stepwise process, except cube your conversion factors each time. Yep. 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 Any questions? Okay. I have 11, 14, 17. No. It's correct. It's correct.
Who was the other answer?
I was just trying to see what was happening with someone's roots. Let me check that one more time.
Yeah, no, you just forgot the second.
I'll read it.
One correction on the first problem that we discussed. Oh, oh, no, that's correct. I see now. Okay.
Oh, okay. Yeah, I tried.
Does anyone need a little bit more time on this? Any questions? Okay, to ensure we're all on the same page, let's come together as a class to discuss this problem. So if I could have everyone's attention up front, let's talk a little bit about this conversion. In general, what I'd like you all to do is to be practiced enough at this to be able to do about 3 of these types of conversions in a 10-minute quiz. So you should be comfortable doing these pretty quickly. So let's start a little bit and let's talk about our conversion. So on the top, what units are we starting off with? Centigrams. Okay, and what units are we trying to reach? Milligrams. What are our intermediate unit? What's our base unit? Grams. Yep. Okay, so on the bottom, what is our starting unit? Yep. So we have 1 over millimeters cubed. And our end goal is what? Yep, 1 over centimeter cubed. Okay, what is our base unit?
1 over meter.
Yep, 1 over meter cubed. Okay, perfect. Now that we have our problem solving map prepared, I'm going to write out my starting value with the units. Okay, now if I want to go from centigram to gram, what units need to be on top? Grams. Okay, and what units need to be on the bottom? Centigrams. As a general rule, you're always going to put a 1 next to the prefix unit and a power of 10 next to the base unit. How many grams are in a centigram? 10 to the negative second. Any questions from the back? Okay, let's continue on. So we're going from grams to milligrams. What units need to be on top? Milligrams. Okay, and in 1 milligram, there are how many grams? Yep, 10 to the negative third. Now on the bottom, we have a composite unit. So we're gonna have to be a little bit careful here. So in order for millimeters cubed to cancel, let's ignore the cube just for a moment. So what do we need on top? Millimeters. So and what do we need, or what do we want on the bottom? Meters. And in 1 millimeter, there are how many meters? Yep, 10 to the negative third. Now, since this is a cubic unit, what do we need to do to this conversion factor? Cube it, exactly. Don't forget to cube your cubic conversion factors or you'll get the wrong answer. Okay, now what do we need at the end? What's our final, what do we need on the bottom? Yep, so we need centimeters on the bottom, and in 1 centimeter, that corresponds to how many meters? Yep, 10 to the negative second. Okay. Yes, so because we're dealing with cubic units, we then have to cube our conversion factor. Okay, now we're ready to punch this into our calculator. I'd like you to take about 1 to 2 minutes to try entering this into your calculator on your own. On the exams, you won't always have me to enter things into the calculator, so I want to make sure you're comfortable doing this on your own. So take about a minute to a minute and a half, punch this into your calculator, and then we'll discuss in a moment. Yes?
Is it okay if I did it like this?
Yes, that's fine. That's fine. Oh. Wait. Oh, so the centimeters need to be on the bottom. But there's 10 to the negative second meter per centimeter. Does that make sense? Otherwise, it's perfectly set up. So, with that time complete, would someone like to raise their hand and volunteer and answer once you punch this into your calculator? Yes. 1.7 times 10 to the 6th. Perfect, perfect. What I greatly appreciate is that you retained the units. If you don't write the units in the final answer, it's incorrect. Okay, so let's show how we do this in the calculator. So what's the first number that we're going to enter? 170. Okay, so we have 170 in our calculator. That's easy. What are we multiplying it by? Yep, 10 to the negative second. Okay, so we multiply it by 1 EE negative 2. So you should get 1.7. Again, you're getting 1 EE negative 2. Everyone okay so far with that? Okay. What are we dividing by now? Yep, 10 to the negative third. We're dividing by 10 to the negative third. So we're going to divide by 1 EE negative 3. Okay? So you're hitting 1 EE negative 3, and then you hit the equal sign. And you should get 1700. Everyone good so far? Okay. So what are we dividing by next? 10 to the negative third cubed. You can either multiply this out before you enter in your calculator, or you can do it the long form way. So to do that, you're going to hit the divide sign, then parentheses. Then, since we're dealing with 10 to the negative third, we're going to enter 1 EE negative 3. Everyone good so far?
Yes.
You're then going to hit the second button and 1, the cube function. And you should get the following very, very large, well, very, very small number. Then you're going to hit the equal sign. You should get 1.7 times 10 to the 12th if you did everything correctly. Everyone following so far? Again, this is why I can't stress enough. Please bring your calculator to every session. Okay, what are we multiplying by next?
10 to the negative.
Yep, 10 to the negative second cubed. Okay, so that's straightforward. All we have to do is hit the multiplication symbol, then parentheses. So we hit 1 EE negative 2, and then to cube it, we hit second, and then 1, which is the cube function. Any questions? You then hit the equal sign, and you end up with the following large number that I'm going to convert to scientific notation by hitting second and then 5. So we have 1.7 times what power of 10?
10 to the 6.
10 to the 6th. So as we see, it perfectly matches our your classmate's calculation, and it's even written with the right number of sig figs, so it's quite good. Any questions on this example? If you're having trouble with any of these, you're going to need to practice these over the course of the weekend, as we'll be having a quiz next class session on it. You'll see about 3 of these on it. Okay, as we still have about an hour remaining, 50 minutes to be exact, we're going to continue on and complete this chapter by talking about significant figures, certain digits, and uncertain digits. So, what do we mean by significant figures? So this is really important as it has to do with handling data properly. So, when you make a measurement, there are 2 types of digits recorded in a measurement. There are your certain digits. These are explicitly recorded on the instrument, or digits explicitly marked by a graduated mark. We'll talk a little bit about what that definition means in a moment. The other subclass of digit is known as an uncertain digit. So the uncertain or estimated digits are digits not marked by a graduated mark, and the estimated digit is always going to be the last digit in a measurement. The total number of digits reported in a measurement are the significant figures. So for example, in the value 50.1 centimeters, the 50, these are our certain digits, while the last digit, the 0.1, is the estimated digit. In total, we have 1, 2, 3 digits. So we have a total of 3 significant figures. So another definition of significant figures is the number of digits reported in a measurement. In general, if you have more significant figures, you're dealing with a more precise measurement. For example, if we compare 5.0 versus 5.000. Let's do grams. Which of these two measurements has more significant figures? The one on the left or the one on the right? On the right. Yeah, the one on the left has 2 sig figs. The one on the right has 4 sig figs and is more precise. Okay, so let's try to look at another example of this. Let's try to identify how many significant figures the following measurements have and which measurement is the most precise. So let's start with this measurement shown here, 15.00. How many sig figs do we have? How many total digits have we reported? 4. So it has 4 sig figs. Okay, would someone like to volunteer? What about 2.0? 2 sig figs, yep. 15.000, 5 sig figs. So which of the following measurements is the most precise? The last one, yep. Why? It has the most significant figures, exactly. Okay, any questions on that? Okay, let's continue on. So we're now going to talk a little bit about taking measurements using graduated devices. So what do I mean by graduated devices? These are devices with markings indicating an increment of a unit of measurement. So each of these little marks, each of these little tick marks, for example, in this ruler, represents 1 centimeter. So the many common graduated rulers have 1 centimeter increments. Now, following our definition of certain versus uncertain digits, or certain versus estimated digits, the certain digits are those explicitly noted by the graduated increments. So if each of our increments, for example, in this ruler represents 1 centimeter, we can report for certain digits up to the 1 centimeter value. For example, in this case, we have 60, 61, 62, 63, 64. So we can say our length is about, the length of this object is about 64 centimeters. These are all of our certain digits. They're explicitly marked by a tick mark or a graduated mark in our instrument. Does that make sense? Now, the uncertain digits or our estimated digits are those not explicitly marked. They are estimated between the graduated marks. So the uncertain digit is the last digit that is estimated between the graduated marks. So for example, looking at this ruler, is our length exactly 64 centimeters or is it a little bit more? A little bit more, right? Would someone like to take a guess? 64 point what? 1, 2, 3, 4? 3, sure. Let's do 64.3. We are estimating the length by looking at a smaller subdivision between the graduated marks. So in general, your estimated digit will be 1/10, or estimated to the place of 1/10 of the smallest graduated mark or tick. So let's talk a little bit about that rule. You can report estimated digits up to 1/10 of the smallest graduated mark, which I like to call a tick mark. So for example, in this ruler, what does each tick mark represent? What do each of those little graduated marks represent? 1 centimeter, right? So if we have 1 centimeter, so all we have to do is take 1 centimeter and we're going to divide it by 10. And that in turn gives us 0.1 centimeters. So this tells us we can report up to what decimal place? First, or the 10th place. Does that make sense to everyone? So depending on the graduated marks and what graduated device you use, you will report a different number of certain digits and estimated or uncertain digits. Does that make sense? Okay. Let's do a few more examples. Let's take a look at ruler number 1. And our first order of business is to figure out the value of a tick. So we're starting off at 60 and we're going to 70. And let's count how many graduated marks are between 60 and 70. 1, 2, 3, 4, 5, 6, 7, 8, 9. It takes a total of 10 graduated marks to go from 60 to 70. In other words, 10 ticks are equal to how many centimeters to go from 60 to 70? 60 to 70. What's the difference between 60 and 70? 10. Yep. So this is 10 centimeters. So for 10 ticks, we go 10 centimeters. So then we know that one tick mark, one graduated mark on this ruler represents how many centimeters? 1. One tick is 10 over 10 centimeters, which is 1 centimeter. Okay? Now from the perspective of the estimated digit, we know we can estimate up to 1/10 of a tick. So 1/10 of a tick is 1 centimeter over 10 or 0.1 centimeters. Okay? With that established, let's try to take a measurement. So what would we expect to be the reasonable length of this piece of wood? So what tick mark are we past? 64. Okay, so we can report certain digits of 64. Would someone like to propose an estimated digit for the length? Sure, 0.3 or 0.2. So 64.3 centimeters. So this reports your measurement with the correct number of significant figures for that graduated device. Yes?
So say you were to quiz us on this and we had a similar problem to this where we had to give an estimate for the last one. Does it matter if like I had 3 and somebody else has 2?
No, you're allowed to have variation up to the estimated digit.
Just as long as it's 3.
Yeah. As we've seen from discussions and input from the class, your classmate may report 64.2. The estimated digit inherently has variation or uncertainty, so it's perfectly tolerable. Yep. If there's variation in the certain digits, I will mark it off. So if you said 62.3, then that would not be correct. Any other questions? Okay, so let's try looking at the second ruler. And let's subject it to the similar set of analysis. So my question to all of you, to go from 60 to 70, that is how many centimeters to go from 60 to 70? Yep, 60 to 70. So in 10 centimeters, that corresponds to how many ticks? Oh, looking at this ruler? Oh, how many graduated marks do we see between 60 and 70? Well, like if I'm moving from 60 to 70, how many graduated marks do I move across? One. It's just one tick. So to go from 60 to 70, I step over 1 graduated mark. Okay, perfect. So now that we have that established, 1/10 of a tick in this case is equal to 10 centimeters over 10, which is 1 centimeter. So we observe variation in the ones place. So would someone like to provide me an estimate for the length of this ruler? There are very few wrong answers in this case. So how many digits can we report up to? What place can we report up to? Sure, 64 would be fine. 6 would be a certain digit, and we'd estimate that it's about 64. Does everyone notice how we can only report up to the ones place because we can only report up to the estimated digit of 1/10 of a tick? Would someone like to provide another measurement? 63, sure. Yep, that's also correct. And as we notice, we see variation in what digit? The ones place, which is called the uncertain or estimated digit. So we see variations in the estimated digit, typically of about 1 unit of the estimated digit. Now, as we can notice in these two measurements, they have different numbers of significant figures, right? So depending on the instrument used, your measurement will have a different number of significant figures reported. So you really need to be careful with how you report and represent your data, as it tells everyone a little bit about how your data is collected. So let's talk a little bit next about precision. So precision is a measure of the variability or deviation in a data set. Measurements with large numbers of significant figures are considered more precise. And the reason for that is the estimated digit is smaller relative to the main measurement. So let's look at two examples now. So 64.3 centimeters versus, let's stick to ones that we've seen before, versus 64 centimeters. So in both of these examples, we'll observe variation in our estimated digit. So this 64 is plus or minus, what's our estimated digit? What place is our estimated digit in? Tens, ones, tenths, what place is it in? Ones. So it'd be 64 centimeters plus or minus 1 centimeter. Well, this is 64.3 plus or minus 0.1. Does everyone notice the distinction in how the variation changes depending on your estimated digit? Now, what is larger? If we compare 1 over 64 to 0.1 over 64.3, which estimated digit has the which of these two measurements has the smallest amount of variation? So this one on the right, 64 plus or minus 1. It's varying in the ones place. This 64.3 is varying in the tenths place. Which of these two measurements has the larger amount of variation, larger amount of uncertainty? The one on the left or the one on the right? The one on the right, 64.3. It has less sig figs, it has a larger amount of uncertainty, and it's less precise. So let's label that as less precise. Does that make sense? Okay, so let's keep going with this. I'm going to ask you a relatively innocuous question. This is similar to what you'll see on potentially a quiz, though there may be differences. How should the following length be recorded for a centimeter ruler? So take a moment and try to record the length. It does take a few steps.
We see how between 1 and 2, there's 5 and 6, right? So then, oh,
So would anyone like to volunteer to provide a measurement? Don't be shy to raise your hand. Oftentimes, sharing potential measurements can help me identify and see what the class is thinking.
1.46.
Let's see. So we have 1.46 centimeter. Can I have another input? We'll talk about them once I've collected a few, so don't worry. Yes. Can I have another input? Don't be shy to share. Yes. 1.25. Okay. Would anyone else have another measurement that they'd like to take? Yes. 1.27. Okay. Would anyone else? 1.43. Okay. Anyone else? Okay, so let's talk about this. I'm not going to provide feedback on these just yet, but let's talk about it individually. So first and foremost, from 1 to 2. So in 1 centimeter, it took us how many tick marks? So counting 1, 2, 3, 4, 5. So 1 centimeter, we had to move across how many ticks? 5. Yep, so 5 little tick marks. So then 1 tick is equal to 1 over 5 centimeters, which is 0.2 centimeters. Okay? As all of these measurements have correctly noted, 1/10 of a tick is equal to 0.2 over 10, which is equal to 0.02 centimeters. So we can report up to the 100th place. Okay? Now, looking at this, what tick mark are we past? What tick mark are we past? 1, 2, 3, 4. What tick mark are we past? The first, second, third, or fourth? Second. So then, what this is really saying is this second tick mark is 1.4. So we know our certain digit is at least 1.4. So let's write that down. And then we can estimate up to 1/10 of a tick. So based on our estimation, I would estimate it to be about 1.46 centimeters. Now, just a stylistic note, and this is really nitpicky, but nonetheless, notice how this 1/10 of a tick is a multiple of 2. So this is the maximum precision we can report to. So can we report an odd number in our last decimal place? Can we report odd numbers if our maximum precision is an even number? No. So even though 1.43 is technically okay, ideally the last number needs to be a multiple of the maximum precision. That's very nitpicky, but essentially it's the fact that 1/10 of a tick only goes up to 0.02 centimeters. We can't report precision smaller than that. And this 1.43 is reporting a precision greater than 0.02. Does that make sense? Okay, so really just make sure you count your tick marks. And that's what this question is designed to help tease out. Any other questions on this example? And thank you all for sharing. This is really informative, as oftentimes it helps me see the logic behind people's solutions, and it helps me address that logic when I'm talking about my solutions. Any questions on this example? Okay, let's keep going. So all instruments, even if they're non-graduated devices, have an inherent uncertainty. There's an inherent uncertainty in their measurements. This is also called error. So in this case, the last digit reported is the estimated digit. So for example, the balances that you see, a typical top loading balance reports values up to the 100th place. So what is our estimated digit going to be? What's the last digit? What place is our last digit in? 100th place. The top loading balances, what is the last digit reported? What place is it in? 1000th place. Which of these two devices is more precise for measuring mass? The second one. Why? Does it have more sig figs? Yes. So just to showcase that, this has 4 sig figs. This has 5 sig figs. Okay. So every instrument has an inherent uncertainty, at minimum equal to 1 unit of the estimated digit, if not more. Okay, so let's keep going. Let's now talk a little bit about glassware that we use to measure volume. So volume is the space occupied by matter. So let's talk and let's look at some common pieces of volumetric glassware. So the first one, which isn't technically a device for measuring volume, a beaker is mainly for holding liquids and for very imprecise volume measurements. The beaker is this piece of glassware shown here. A burette is a specialized piece of glassware for precisely dispensing variable volume. So the burette is shown right here. We'll see when we look at the tick marks for each of these graduated devices why a burette is more precise. C, this large yellow container, is our volumetric flask. It's for precisely measuring a fixed volume. So when you hear the word volumetric, what that's telling us is a fixed volume. Any questions so far? Okay. The graduated cylinder, and many students mistakenly think that this device is precise. It's for dispensing variable volumes with medium precision. It has a reasonable level of precision, but it's not as precise as the more specialized pieces of glassware. And the graduated cylinder is shown here for letter D. The volumetric pipette, which is shown in green, is designed to precisely dispense an exact volume. It's designed to transfer an exact volume. Finally, F, sorry, it should be an Erlenmeyer flask. And again, just like a beaker, the Erlenmeyer flask, which is shown here, is designed for imprecise volume measurements. I should not see you measuring out exact quantities in a beaker or an Erlenmeyer flask, or you will immediately have points deducted on your report if I don't see you remeasure it. Okay, let's keep going and let's talk a little bit about measuring volumes in volumetric glassware. So, first and foremost, the volumes are measured from the bottom of the meniscus at eye level. You have to be at eye level with the water level in your volumetric glassware, or you will not be able to take a precise measurement, nor an accurate measurement. This is due to the fact that liquids refract light, and you will not get an accurate location of the top of the liquid layer if you're looking at it from above or from far below. Does that make sense? Okay. So the meniscus is a curve formed as a result of liquid interacting with the container. This is a consequence of intermolecular forces. And does everyone see this little band here? Do you notice how there's a little curve in the liquid layer? Okay. So first and foremost, let's zoom in as much as we can. And in order to measure the following volume, pretend you're just staring at this piece of glassware. First and foremost, our goal is to identify the value of each graduated tick. Okay, so looking from 8 to 9, so from 8 to 9 milliliters, so what volume is between 8 and 9 mils? I mean, just like if I went from 8 mils to 9 mils, how many milliliters have I traversed? So what's 9 minus 8? 1. Yeah, so we have 1 milliliter. Okay, and how many of these little tick marks do you see? Let's count them. How many total tick marks do we see from 8 to 9? Yeah, we see a total of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 ticks equal to 1 milliliter. You're going to be very, very fast at figuring out the amount of each graduated tick in order to quickly and efficiently make measurements. Okay, so we know 10 ticks are equal to 1 mil. We know 1 tick is equal to 1/10 or 0.1 mil. Now we next need to figure out the maximum allowed precision, which is 1/10 of a tick. And 1/10 of a tick is 0.1 over 10, which is 0.01 mils. Okay, with that established, we are now ready to continue on and make a formal measurement. So let me erase here. So drawing a line at the bottom of the meniscus, what tick mark are we past? What tick mark is the bottom of the meniscus past? What was that? The third tick mark, exactly. So we can estimate it to be about 8.3. And would someone like to provide the estimated digit? 1, sure. Are we missing something? Milliliters. Numbers do not have inherent meaning in our physical world. They require units. Okay. Any questions on how to make measurements from volumetric devices? You'll be doing this a lot and expect to see actual pictures from lab setups. Okay, let's talk next about reading barrettes. Barrettes are exactly, or well, they're similar to graduated cylinders, except a key feature of barrettes is that they measure the volume dispensed. You can think of a barrette as an upside down graduated cylinder. Do you notice how we're counting from 30 to 31 going down the barrette? So then, I'd like you all to take a moment and try to figure out the value of a single tick. And I'd like you to try to estimate a measurement for this barrette, keeping in mind that barrettes measure the volume dispensed and they count from top to bottom. So just take a moment and we'll discuss in about a minute. So would someone like to volunteer a measurement from this barrette? Yes. 32.5 milliliters. Okay. Would someone else like to volunteer another measurement? Yes. 30.25 mil. Would someone else like to volunteer? What was that? Don't be shy. 30.13. Okay. Any other measurements? Okay, so let's discuss this. So first and foremost, counting our ticks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a total of 10 ticks. So from 30 to 31. So we went from 30 to 31 milliliters. What total volume? Yeah, we have 1 milliliter is equal to 10 ticks. So then we know 1 tick is equal to 0.1 milliliter. Now let's figure out our estimated digit. We know that 1/10 of a tick is equal to 0.01 milliliters. So if I had to pick and make a measurement, just to be clear for looking at this mark here represents 30.1. What mark are we past? The first, second, third? Second. So what are our certain digits going to be? 30. Yep, so we have 30.2, and then can we estimate an additional digit? Yes, and what will we estimate? 5, sure. 30.25 milliliters seems perfectly fine with me. Does that make sense to everyone? Okay. So with that out of the way, let's now take a look, and I'd like you to tell me from this picture, which is something you'll see when you perform a titration, which of the following barrette measurements are correct. So take about 2 to 3 minutes, and please be careful, not all barrettes have the same tick mark distribution. Barrette, yeah, you read from top to bottom. So above 24 is 24. Above 24 is, yeah. Yes, that's correct. Any questions? Any questions? Any questions? So can I have a few volunteers? Just as a show of hands, how many students recommend the first response? Don't be shy to raise your hand. Anyone recommend the first response? No? Anyone recommend the second response? Anyone recommend the third response? Okay, good, good. Anyone recommend the fourth response? Okay, so let's talk a little bit about this. So we're counting from 24 to 25. So we count, let me use a really bright color for this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in 1 mil, we have 10 ticks. So 1 tick is 0.1 mil. Let's now figure out the maximum amount of digits we can report. 1/10 of a tick is 0.01 milliliters. Okay, so with that established, let's try to report our certain digits. So what tick mark are we past here? We are past what tick mark? The bottom of the meniscus. So let's count. Remember I said 1, 2, 3, 4. What tick mark are we past here? If I drew this line here, 2, the second tick mark. So we can write our certain digits as 24.2, and then can we estimate an additional digit? Yes, so this would be 24.20 milliliters. I would be careful about waiting for other classmates to raise their hand because the consensus is not always the correct answer. Okay, so I'd like you to record the following volume measurement. So just take a few minutes to work on that. Any questions? So, as customary for this section, can I receive some input from the class? So would someone have a preferred measurement for this? Yes.
10.67.
10.67, okay. Yes.
I was just gonna say
Okay. Would anyone else like to volunteer? Yes. 10.78, okay. Would anyone else like to volunteer? 10.68. Anyone else? Okay, so let's talk about this then. First question, is this a barrette or a graduated cylinder? Graduated cylinder, it's read from bottom to top. You can tell by the fact that 10 is below 11. Okay, the next question that we have, from 10 to 11 milliliters. So 1 milliliter, that's equivalent to how many ticks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 milliliter is equivalent to 10 ticks. To figure out how many digits we can report up to, 1/10 of a tick. Oh, whoops, we got a little bit ahead of myself there. First and foremost, we need to figure out the value of a tick. 1 tick is 1/10 of a mil, which is 0.1 milliliters. We next need to figure out our maximum reporting limit, which is 1/10 of a tick, which is equal to 0.01 milliliters. Okay, so what graduated mark is the bottom of our meniscus past? What graduated mark? So counting 1, 2, 3, I can't, the writing will be too small. 1, 2, 3, 4, 5, 6. Are we past the 6th or are we past the 7th? 6th. You measure from the bottom of the meniscus. So we can report 10.6 and then we can estimate one additional digit. And what digit are we estimating? Well, sure, 7. That's fine. Key thing, make sure to include the units of milliliters. Does that make sense? Okay. So just a special case for volumetric pipettes and volumetric flasks. Unless otherwise printed, volumetric flasks report up to 2 decimal places of precision. So when you see a 25 mil volumetric pipette, it's really saying it reports 25.00 milliliters. Likewise, a 100 milliliter volumetric flask will report up to a precision of 100.00 milliliters. Does that make sense? Okay. So we won't have time to cover this. So we'll pick this up next class session.